Okay, this is going to be Chapter 8, and this is going to be the first part of Chapter 8, which is going to be sections 1 through 5. All right, so it starts out and we have some common gases. Those would be the noble gases, which are the very last column on the periodic table, group 18. There's also your diatomic gases, the hydrogen, nitrogen, oxygen, fluorine, chlorine. And then there's also many oxides of nonmetals like carbon monoxide, carbon dioxide, and nitrogen monoxide, and so forth. A lot of the gases are responsible for environmental and health concerns. Those would be methane, the chlorofluorocarbons, which are responsible for the depletion of the ozone, nitrogen oxides that are found in smog, and many volatile organic compounds. And those would be things that you're going to find in paint thinners, varnishes, things like that. We're going to first look at the kinetic theory of gases. And the kinetic theory says that gases move in random motion with high velocities. And even though the motion is random, they're always in a straight line path. It also says that these molecules within a gas have no attractive or repulsive forces on each other, so they move independently, and that the volume of those individual particles is very, very small compared to the entire container. These particles are always in motion, and that if we increase the temperature, that's going to increase the kinetic energy of the gases, or in other words, the speed of the particles. So if the temperature is cold, that means the particles don't move very much. If the temperature is a lot hotter, then those particles are going to move very quickly. There's 4 different properties that we're going to measure for a gas. Those are going to be pressure, volume, temperature, and amount. And so pressure, we're going to use the symbol P. Volume, we're going to use the capital letter V. Temperature is going to be the capital letter T. And the amount is N, which stands for the number of moles. Now for pressure, the units that we're going to be using could be atmospheres, millimeter, torr, pascals. So there's going to be a lot of different units. Volume could be liters, milliliters, centimeters cubed. I would say most of the time it's going to be in liters or milliliters. Temperature, we are going to have to use Kelvin, although a lot of times they might give it to you in Celsius. It has to be in Kelvin when you use the gas laws. And the amount is going to be moles. So even if they give you grams or kilograms or anything else, it's going to have to be in moles. All right, when we talk about pressure, pressure is the force that is acting on an area. So the units, the SI units that we're going to use are pascals. And other units that you've probably heard about are PSI, which is pounds per square inch. So the pound being the force and the area being the square inches. So if you think about those gas particles moving around, they're going to hit the side of the container with a certain amount of force. And depending on how big of an area they hit, that's going to dictate what the pressure is going to be. Now, down here, these are some conversion factors. So 1 atmosphere is 760 millimeters of mercury. 1 atmosphere is 760 torr. 1 atmosphere is 14.7 psi. And 1 atmosphere is 101.325 kilopascals. And again, these are conversion factors, so those won't be counting towards your significant figures. So here's an example of just converting. So if you have 475 millimeters and we want to convert it into atmospheres, we'd start with our 475, and then we would use the conversion factor that 1 atmosphere is 760 millimeters. And I want to put the millimeters on the bottom so that these would cancel. So I take 475 times 1 and then divide by 760. My original number has 3 significant figures, so my final answer has 3 significant figures. Okay, now we often talk about atmospheric pressure, especially if you would watch the news, they're going to give you what the pressure is every day. And the atmospheric pressure is caused by the air that is all around us. Gravity is pulling on that air toward the center of the earth, so that air is exerting pressure. And sea level is 1 atmosphere of pressure. So here's at sea level. Now you can see up here at the top of a mountain that the atmospheric pressure is less. And if you think about it, here is the air that's down here. So it has a lot more air up above pushing down on it, so there would be more pressure. Just like if you had a bunch of people that all piled on top of each other, the person on the bottom is going to feel the most pressure. So at sea level, we said that it's 1 atmosphere. We know that the altitude is going to affect that. If we are at a higher altitude, there's less pressure. The lower the altitude, the more pressure there's going to be. And we know the weather has something to do with it. If it's usually the atmospheric pressure is higher on a rainy day than it's going to be on a sunny day. And the atmospheric pressure is going to vary even throughout the day. Okay, so here's a chart that has altitude and atmospheric pressure. So you can see at sea level, we said that it's 1 atmosphere, which is 760 millimeters, and that as we go to higher and higher altitudes, that the atmospheric pressure is less. Okay, the way that we measure pressure is with a tool called a barometer. And in most of the labs, and in our lab at DMAC, we have a barometer that looks like this. So it's got a little pool of mercury down in here, and then there's a tall column, a glass column that sits inside of it. So as the air pushes down on this pool of mercury, the mercury has nowhere to go except for to rise up in the tube. And next to the tube, there's going to be a ruler, and that ruler usually has millimeter markings on it or inch markings on it. So we could read it in inches of mercury, and that's what you would find on a newscast. Or we would be reading it in millimeters of mercury. Okay, so now we're going to look at the gas laws. The first gas law is Boyle's law. And Boyle's law says that the pressure of a gas is inversely related to the volume. Now what that means is that if the volume gets smaller, so here you can see a piston, and if we push down on that, the volume of the gas gets smaller. Well, if the volume of the gas gets smaller, that means these particles are going to be hitting the sides more often because they have less area in which to hit. So the pressure is going to increase. So if they are inversely related, that means they do the opposite. So as volume gets smaller, pressure gets bigger. And in order for this relationship to hold true, the temperature and the amount of particles, the moles, are going to be constant. So if we're going to look at an inversely proportional relationship, then we say P times V is a constant. So you can see here, if I take 8 times 2, that's the same as 4 times 4. So the relationship that we have is P1V1 equals P2V2, meaning the pressure and the volume now is going to be the same as the pressure times the volume later. So here's an example. It says we have a sample of nitrogen gas has a volume of 4.2 at 1 atmosphere. And if the pressure is decreased to 0.75, with no change in the temperature or the amount, what would be the new volume? So if we use our P1V1 equals P2V2, we have a pressure of 1, a volume of 4.2. Later, the pressure is 0.75, and we want to find the new volume. So we would multiply these two. So 1 times 4.2, then we would divide by the 0.75. And that's what it shows here, 4.2 times 1 divided by the 0.75. And this has 2 significant figures in all of these, so my answer has 2 significant figures. All right, Charles's law is our second gas law. And for Charles's law, it says that the temperature, and of course this is Kelvin temperature because it always has to be in Kelvin, is directly related to the volume. Now this time they're directly, which means if the temperature gets bigger, so does the volume. Okay, so if you heat something up, it's going to expand and the volume is going to get bigger. And since we have 4 variables, if these are the 2 we're looking at, the other 2 are going to be constant. Now, since these are directly related, last time when they were inverse, we multiplied. Since these are directly related, we're going to divide. So V1 over T1 equals V2 over T2. And these temperatures have to be in Kelvin. All right, so here's an example. A sample of neon has a volume of 3.1 and a temperature of 12. Okay, so I'm going to do V1 over T1 equals V2 over T2. So I have a volume of 3.1 and I have a temperature of 12. I can't use 12. I have to add 273 to get it into Kelvin. So this is going to be 285. Find the new volume. So I want to find the new volume when my temperature is 32. So 273 plus 32 is going to be 305. Then I want to cross multiply and divide. So I'm going to be taking 3.1 times 305 divided by the 285. So you can see here I took 3.1 times 305, then I'm going to divide by 285. Okay, and I got 3.3 liters. That's this answer. And it's got two significant figures because 3.1 has 2, 305 has 3, 285 has 3, so I need 2, which is the least amount. Okay, next gas law is Gay-Lussac's law, and this is the relationship between pressure and temperature. And Gay-Lussac says that the pressure directly related to temperature, and again it's got to be in Kelvin. So these are directly related, which means they do the same thing. So as the temperature gets higher, the particles move faster, they're going to hit the container more often, so we're going to have more pressure. So as one goes up, the other one goes up. And since we're looking at pressure and temperature, volume and the amount have to be constant. And last time we had V over T if they were directly proportional. So since these are still direct, it's going to be divided. So P1 over T1 equals P2 over T2. And again, those temperatures have to be Kelvin. They will not work if you don't. So here's an example. So I'm going to set it up as P1 over T1 equals P2 over T2. So it has a pressure of 2 when my temperature is 18. So 273 plus 18 is 291. And we want to know the new pressure when the temperature is 62. So 273 plus 62, 335. And again, cross multiply and then divide. So I'm going to take 2 times 335 divided by 291. And 2 sig figs, 3 sig figs, 3 sig figs, I'm going to get 2 for 2.3 atmospheres. And since this pressure was in atmospheres, this one will be in atmospheres. And it doesn't matter if those were in millimeters as long as they're both the same. So the only unit that you have to be sure of in any of the gas laws is temperature has to be Kelvin. The other units doesn't matter as long as they're the same. Meaning if you're using volume, if one is liters and the other one's liters, it's fine, you don't have to convert. If you have centimeters cubed and centimeters cubed, it's fine. But if you have different volume units or different pressure units, you'll have to make them the same. All right, vapor pressure. So vapor pressure is the pressure that the vapor exerts on the liquid. So this is evaporating. There's going to be vapor up here. And that vapor is going to exert pressure down on the liquid. And that's the vapor pressure. And as the temperature increases, more of these particles are going to have enough energy in order to evaporate. So it means there's going to be more vapor and then therefore more vapor pressure. And the vapor pressure is related to the boiling point. So here you can see on this chart, as the vapor pressure gets bigger, so does the temperature of the boiling point, which means when we say that the boiling point of water is 100 degrees Celsius, it's only 100 degrees Celsius when you are at 1 atmosphere pressure, or 760 millimeters. Water only boils at 100 degrees if you're at 760. And we are not at sea level in Carroll, Iowa, or where I'm at in Exira. So that means that we are not going to boil at exactly 100 degrees Celsius. So when somebody asks you what is the boiling point of water, you need to ask, well, what is the pressure? Because if the pressure is higher, then that means the temperature is higher. So if we think about high altitude, we talked about before, when we have high altitude, that means that the vapor pressure is going to be less. If the vapor pressure is less, that means the boiling point is less. So if you've ever looked at packages of food and they have high altitude directions on them, like if you're going to make boxed mac and cheese, if you're supposed to boil it for 10 minutes when you're cooking it at sea level, if you're boiling water and it's boiling at 98 degrees Celsius instead of 100, if you're at a high altitude, then that means it's not going to cook in 10 minutes. You're going to have to cook it longer. So when you look at those box directions, they'll have special directions for high altitude because, especially if you're boiling things, that temperature is not going to be at 100 degrees like we assume it is on the box. And if you're cooking something at a lower temperature, it's going to take longer. Okay, so that's just what we were talking about here, how the boiling point of water depends on the pressure. And we know that at higher altitudes, we're going to have lower pressure, therefore a lower boiling point. So this one is showing you as the pressure increases, the boiling point, of course, is going to increase. And these are of water.